Okay, go back to the front page, and I want you to write down the equation that's written for the Born-Haber process, because that's one that you should know. And I think you've seen it before, but you specifically need to remember if it's endothermic or exothermic. So basically, this is a setup for understanding how does industry use Le Chatelier's principle. And Le Chatelier's principle is something you already read about. What's the general gist of Le Chatelier's principle? You read about it and wrote down some notes about it from the outline last week. Okay, why would equilibrium shift?
Stress.
If you stress it out, well, how do you stress it out? Pretty much changing any variable would stress out the system. So basically we're saying, hey, the system's already at equilibrium. The rate of the forward equals the rate of the reverse. If I stress it out by changing concentrations or pressure, temperature, or whatnot, it will then shift in a direction to reestablish equilibrium because it wants to become, it wants to get to that equal kind of stable process again. So the Born-Haber process is a way you can actually abuse Le Chatelier's principle to make more of something that we really need. And what is that something we really need in the Born-Haber formula or equation? So, but what do we need? Probably need more. We need ammonia. Ammonia is the way that we actually intake our nitrogen. Taking in our diatomic nitrogen does not happen very well in humans. Nitrogen fixing bacteria from biology, you remember that in like the root nodules? Thank you, biology. I've from 2 years ago. Gosh, okay. So anyway, nitrogen fixing bacteria take in the nitrogen from the atmosphere and we then eat it. Anyway, this is how it can be made artificial or synthetically as well. And so this process is endothermic or exothermic. You see the negative, right, to ammonia? Okay, so delta H is negative 92 kilojoules per mole. All right, so this is one equation you need to know. You also need to know it's exothermic. You don't need to know the value for it, but just know that it's exothermic. So under what two conditions had to be changed to maximize the amount of ammonia made, according to the first paragraph?
Pressure.
Okay, so what happened to pressure? Right, so they increased the pressure, and they did what's the temperature? Decrease the temperature, and then that, in those conditions, it would force the forward direction to occur more readily than the reverse direction, so therefore the amount of ammonia was optimized. Why does it make sense that when I increase the pressure, it shifts to the products? There's less moles of gas over here, so basically, if I'm artificially increasing the pressure, oh no, what have I done? I've caused the system to be stressed out by just creating too many collisions, because pressure is just collisions with what? With the container wall. So if I increase the pressure, I've artificially increased the number of collisions. How would I then decrease the number of collisions to reestablish equilibrium? You go to the side with less moles of gas because they just collide naturally less than the 4 moles of gas over here versus the 2 moles of gas over here. Okay, talk about nitrogen fixation. So there's poor yield. You can't have your cake and eat it too. So like, how do you get more? How do you expedite the process as well as decrease the cost? There are 2 more reactions on the next page. Those are not really ones that you need to know. Yeah. And that's something we're going to get into deep details in just a second. But if you notice it's exothermic, if you wrote this out in a different way, you could write plus 92 kilojoules over here on the product side. And so if you take away, so decrease the temperature, if you take away a product, and we don't think about it that way in AP, we think of it as limiting the amount of energy in the reverse direction, because to go in the reverse direction, you must add 92 kilojoules. Otherwise, it will never occur because this activation energy is too high. But if you take this away, it's going to proceed. It's going to shift right as well to create more ammonia. Okay, so I wanted you to be aware of that. And then under the Le Chatelier's principle in physiology, oxygen by transport of blood. If you people should remember this a little bit. We're also going to talk about buffers next unit. And in the blood, there's a buffer system that keeps your pH of your blood very stable. What is the pH of your blood? I think it said it. 7.4. Okay, so pH should be 7.4. Now, if I take in carbon dioxide will then bond with things in your blood, bicarbonate and or water, and that can actually make acidic conditions or basic conditions. The one we're really focusing on is the one given to you, so this is another equation you probably should write down, is carbonic acid plus carbonate equilibrates to bicarbonate. And then you can probably imagine, I don't know where the oxygen component is, I mean the carbon dioxide, Whenever you intake carbon dioxide, it's going to shift one way or the other. And we're not going to get into the details of how this affects pH right now, because that's our next unit. But whenever you take in carbon dioxide, it's going to shift to one way or the other. One way is more acidic than the other, so therefore the pH could change. But a buffer system eliminates the huge changes in pH, which keeps you alive. So this is another one that's going to be considered a buffer. And so we're really just talking about shifting left, shifting right, and no shift. All right, cool. So hold on to the reading. Let's go ahead and watch the video now, and then we'll hit up the rest of the notes in a second. Their notes are like maybe 20 minutes today. It's not very long. Okay, let's do this for real now.
What would you say is the most important discovery made in the past few centuries? Is it the computer, the car, electricity, or maybe the discovery of the atom? I would argue that it is this chemical reaction. A nitrogen gas molecule plus 3 hydrogen gas molecules gets you 2 ammonia gas molecules. This is the Haber process of binding nitrogen molecules in the air to hydrogen molecules, or turning air into fertilizer. Without this reaction, farmers would be capable of producing enough food for only 4 billion people. Our current population is just over 7 billion people. So without the Haber process, over 3 billion people would be without food. You see, nitrogen, in the form of nitrate, NO3, is an essential nutrient for plants to survive. As crops grow, they consume the nitrogen, removing it from the soil. The nitrogen can be replenished through long natural fertilization processes like decaying animals, but humans want to grow food much faster than that. Now, here's the frustrating part. 78% of the air is composed of nitrogen, but crops can't just take nitrogen from the air because it contains very strong triple bonds, which crops cannot break. What Haber did, basically, was figure out a way to take this nitrogen in the air and put it into the ground. In 1908, the German chemist Fritz Haber developed a chemical method for utilizing the vast supply of nitrogen in the air. Haber found a method which took the nitrogen in the air and bonded it to hydrogen to form ammonia. Ammonia can then be injected into the soil, where it is quickly converted into nitrate. But if Haber's process was going to be used to feed the world, he would need to find a way to create a lot of this ammonia quickly and easily. In order to understand how Haber accomplished this feat, we need to know something about chemical equilibrium. Chemical equilibrium can be achieved when you have a reaction in a closed container. For example, let's say you put hydrogen and nitrogen into a closed container and allow them to react. In the beginning of the experiment, we have a lot of nitrogen and hydrogen, so the formation of ammonia proceeds at a high speed. But as the hydrogen and nitrogen react and get used up, the reaction slows down because there is less nitrogen and hydrogen in the container. Eventually, the ammonia molecules reach a point where they start to decompose back into the nitrogen and hydrogen. After a while, the two reactions.
Can you see how this is being indicated on this graph above? So you can probably imagine the yellow line represents which compound. Oh yeah, it is ammonia. Sorry, I was thinking you put nitrogen, hydrogen first. And this is kind of blended, but it's pink and blue in the first case. So he's actually showing them going to the same concentration, which is not always the case. So this is concentration on this side. But you can see how the rate of the reverse and the rate of the forward are differing throughout until they eventually start to go stagnant, where the rates of the forward and rate of the reverse are going to be equal due to the equal slope, which is getting ready to happen.
Creating and breaking down ammonia will reach the same speed. When these speeds are equal, we say the reaction has reached equilibrium. This might sound good, but it's not when what you want is to just create a ton of ammonia. Haber doesn't want the ammonia to break down at all, but if you simply leave the reaction in a closed container, that's what will happen. Here's where Henri Le Chatelier, a French chemist, can help. What he found was that if you take a system in equilibrium and you add something to it, like say nitrogen, the system will work to get back to equilibrium again. Le Chatelier also found that if you increase the amount of pressure on a system, the system tries to work to return to the pressure it had. It's like the
increase in the pressure causing the volume to decrease was whose law? Boyle's law. P1 V1 equals P2 V2? Yeah?
in a crowded room, the more molecules there are, the more pressure there is. If we look back at our equation, we see that on the left-hand side, there are 4 molecules on the left and just 2 on the right. So if we want the room to be less crowded and therefore have less pressure, the system will start combining nitrogen and hydrogen to make the more compact ammonia molecules. Haber realized that in order to make large amounts of ammonia, he would have to create a machine that would continually add nitrogen and hydrogen, while also increasing the pressure on the equilibrium system, which is exactly what he did. Today, ammonia is one of the most produced chemical compounds in the world. Roughly 131 million metric tons are produced a year, which is about 290 billion pounds of ammonia. That's about the mass of 30 million African elephants, weighing roughly 10,000 pounds each. 80% of this ammonia is used in fertilizer production, while the rest is used in industrial and household use, and to produce other nitrogen compounds, such as nitric acid. Recent studies have found that half of the nitrogen from these fertilizers is not assimilated by plants. Consequently, the nitrogen is found as a volatile chemical compound in the Earth's water supplies and atmosphere, severely damaging our environment. Of course, Haber did not foresee this problem when he introduced his invention. Following his pioneering vision, scientists today are looking for a new Haber process of the 21st century, which will reach the same level of aid without the dangerous consequences.
They're actually looking for one that would decrease the amount of carbon dioxide in our atmosphere to eliminate all human-generated carbon dioxide, not all, but a lot of it to aid in climate change, to aid against climate change, not with it. Okay, so we already heard some of the changes that can occur to equilibrium or stresses that can occur, but whenever we talk about this principle, it is just a principle. It is a statement. When you say shift left and shift right, you are simply telling me which way the equilibrium position is going to be changing towards. It does not explain anything. So I need you to learn how to explain a bit more, because back in honors chem, you literally learn shift left, shift right, no shift, and that's it. Now we need to understand the concept of why it's shifting. And so I'm just going to add a bit more detail to this. So I recommend you write down pretty much everything I write, because it's an explanation based, and then we're going to draw a graph and then we'll be done. We have a web quest after this. So whenever we talk about the principle in general, we already talked about how, hey, we already have equilibrium. We stress it out. When we stress it out, it's going to then shift in a way to relieve the stress. So when it's relieving the stress, it's then going to come up to a new equilibrium position. What the heck does that mean? Equilibrium position. Anybody got any idea? Right. It's going to establish new concentrations of reactants, products. Okay, but what about the K value? Will the K value change when I change the concentrations of these reactants and products? No, because the ratio between them, I can keep the ratio between the reactants and products the same. The only thing that will ever change equilibrium, so right here I say not a new K, okay? So no change in K EQ. The only thing that will ever change the K for equilibrium is temperature changes, because just like little k from rate laws, the rate constant, or rate law constant, that little k is dependent upon temperature, so is this one, because how is this one derived? You guys remember that from day one notes without me? Do you remember how this k is derived? Big K equilibrium is the K of the forward reaction over the K of the reverse direction for little k's from kinetics. Maybe you remember that, maybe don't, but this is big K is equal to KF over KR, so K forward over K of reverse direction for the kinetics rate law. And so if these are temperature dependent, then this one is obviously also temperature dependent. Okay, so we're going to establish these new equilibrium concentrations, which would therefore not change our K, but there's a reason why they're changing. So I'm going to start with adding a reactant. Adding a reactant, what happens to the forward direction? The rate of the forward direction. Go for it. Why? So if I increase reactant concentration, what happens to the rate of the forward direction?
It increases.
Right, so I'm increasing the rate of the forward direction. Okay, well, now all of a sudden, what have I done? Hold on, let's backtrack. What is the definition of equilibrium? Has to do with rates.
When the rate of forward reaction equals the rate of
Right, so rate forward must equal rate reverse to be at equilibrium. Well, if I've just increased the rate of the forward direction, now I'm not at equilibrium. So in order to reestablish that, I must allow for these reactants to react. When I allow for the reactants to react, they react and expedite the process to the right, so shifting right. So basically, when I increase reactants, the rate of the forward increases. You must react reactant species, and so to do that, you have to proceed right or shift right. So SR means shift right. So there's the background, that's the reasoning behind it. Another kind of similar set of reasoning is, relate this back to Q. You know, Q is set up the same way as K, as product concentration over reactant concentration. If I increase the reactants, what happens to the Q value? So remember, reactants are numerator or denominator in Q? Or in K? Denominator, right? So quick reminder, Q is just concentration of products over concentration of reactants. So if I increase the concentration of reactants, I'm increasing the denominator, so what happens to Q? Smaller. Okay, so Q is low. So how do I get Q back up? Do you make more products or do you make more reactants? More products. So when you say make more products, you're telling me to shift right. So that's another way to think about it. And comparing to Q is much easier because you understand like the concentration of products and reactants. That only thing that you can't do Q with like pressure or with temperature because it's not related to the variables within Q. Okay, so then tell me your logic on adding a product. So kind of the same way I have. Increasing products does what? So increases the rate of the reverse. So in order to consume products, you have to go in the reverse direction, and that would be us doing what? Shifting left. And you're doing that actually to, like Jack said, increase the number of reactants. So when you shift left, you are going to be increasing the number of reactants just so they can catch up to the rate of the reverse. Because increasing reactants means they're going to collide more. When they collide more, they go back to the product side. So it's all about collisions, and so I didn't write that down. But collisions are what's driving this rate changing in order to disrupt equilibrium. What's that? SL, shift left.
Oh.
Okay, so same story, just slightly opposite. Removing a product. So you can actually remove a product simply by taking it away. So like one of the gases, let's say we could take away or siphon off ammonia from the Haber process, and that we could store into another container, but in that closed container where the reaction's happening, if I take away a product, I can force the reaction to go in the forward direction. I can also remove a product by making it precipitate out. Why precipitating out? Why does that affect equilibrium? It's because originally it may have been aqueous form, and when I precipitate it out, it's in solid form, and solids are not included in equilibrium. So we've essentially taken it out. So removing a product does what to the rate of or does what to the rate in general? You guys tell me which one you're talking about.
Increases the rate of forward reverse.
It's not actually going to intentionally increase the rate of the forward, but it's going to decrease the rate of the reverse. See what I'm saying? So the products control the reverse direction, so you're going to decrease the rate of the reverse direction, which means the rate of the forward happens to be greater than the reverse. It's not that the forward is actually increasing. Okay, so when you decrease the rate of the reverse direction, you're eventually going to start making more and more and more products because the forward is still occurring. So to combat that, actually no, you do. That is actually what happens. Shift right in general because the rate of the forward is greater than the rate of the reverse. So you already know it's going to shift right because you need to make more products. How does that relate to Q? If you decrease products, what is wrong with Q? Or what has happened to Q? Right, so Q is low, and so you must shift right to increase Q back up to what K was, what K, the equilibrium constant K is. I'll do that, just Q expression here. Removing a reactant does what to Q? Remember, Q is products of reactants. What happens when I remove a reactant?
Makes it larger.
It's larger, right, because whenever you remove a reactant, it's products over a low number of reactants, and so that yields Q to be bigger. And if Q is too big, then I need to eliminate the numerator, which means to shift left in this case. So removing a reactant means to shift left, and you know that because you know you want to make more reactants. So I think you know the final answer, you just don't know the explanation to get there, and that's what I'm explaining here. Okay, so now we've got to deal with pressure, and pressure is just simply a condition of gaseous equilibrium. And so just like they did in the video, increasing pressure, so this is Boyle's law, increasing the pressure decreasing the volume causes an increase in pressure. We know that because of Boyle's law relationship. And then what do we talk about in terms of collisions whenever pressure was increased? There's a lot more collisions, and that's why the pressure has increased. So basically, when I decrease the size of my container, my closed system, the collisions occur more readily with the container wall because there's less space to move around. That inherently causes the pressure to increase, so I'll add that as like a stepping stone here. So more collisions, so the pressure then increases. And so if the pressure is too high, according to what the equilibrium pressure was, how do I get the pressure back down? Because remember, you're fixing the stress, you're eliminating the stress, you're, what was the word I used? Alleviating the stress. So if the pressure is too high, how do I get the pressure back down? Right, so you're going to shift the side with less moles of gas. And this is the most, I think, the one that makes a lot of sense, but it's very wordy. So you have to shift to the side with less moles of gas. So let's write down the Haber process again. Ammonia, or nitrogen plus hydrogen gas equilibrates to ammonia gas. How many moles of gas are on the product side? 2 moles of gas here, and how many over here? 4 moles of gas. So if I increase the pressure of this system, which side is it going to favor? Right, the product side. So increasing pressure causes a shift right because I only have 2 moles of gas, and that's going to then decrease the pressure back to what equilibrium's pressure was. If I decrease the pressure, they're like, oh no, I gotta get the pressure back up. So I gotta get the pressure back up, I must go to 4 moles of gas because it's going to inherently collide more, make the pressure go back up to what equilibrium pressure was. This little guy, inert gases, they don't do anything to the equilibrium position, because, so meaning there's no shift. And that's because partial pressures of each of the gases that are already inside, the ratio of them does not change. So tell me, how do you get partial pressure again of a gas? Does anybody remember that equation? Oh yes, you're right. So you're talking about Dalton's law, partial pressure of everything is equal to the total pressure. What about with mole fraction? You guys remember what mole fraction is? What variable it looks like? X, mole fraction of A times P total, that gives you partial pressure. Do you remember that? I'm pretty sure we went over that. If not, I might be lying to you. Anyway, so I'm trying to review with you some too as well. All right, so if K is, let's say partial pressure of A times partial pressure of B over partial pressure of C, and I add an inert gas, which overall makes the pressure higher because there's more stuff, more gases colliding, this partial pressure, this partial pressure, this partial pressure will all change in the same amounts because it's all based off the total pressure, and so it's a ratio based off their mole fractions. So therefore, the ratio is not going to change. The ratio is constant, and that's why it's a no shift. So inert gases don't react, they just add more pressure. Okay. Okay, so far we've got 3 things, and I want you to know each of these 3 change the equilibrium position, but not K. Those 3 change the equilibrium position, but not K. Give me a thumbs up or something. I know I'm talking a lot, so I think I'm giving you time to write down what you need. Okay. So these are the last 2, and I think we have already discussed the catalyst information here. Catalysts are going to speed up both the reverse direction and the forward direction. And we mentioned the fact that, that doesn't actually do anything to equilibrium. We just get to equilibrium faster. That's it. So you can just say that catalyst part's just really only related to kinetics. So we get to equilibrium faster. But in the end, there's no shift to the equilibrium position. The temperature one is the one I just spend all the time on. And there's some writing to do on that one, so I'll stop talking. So these are methods of helping to explain your take on Le Chatelier's. Okay, so temperature. Temperature is the one that's going to be able to change the K number itself, the equilibrium expression constant itself. And it's going to depend on if it's an endothermic reaction or an exothermic reaction. So when I say depends on the enthalpy of reaction, that means endo or exo. And so I'll give you an example. Let's do A plus B plus 100 kilojoules yields C, or equilibrates to C. So we'll stick with that example. So is this an endothermic process or exothermic?
And
Definitely endothermic, because you can see the heat is on the reactant side. So if I increase, let's just go with the scenario of increasing the temperature. If I increase the temperature, I'm giving energy to the reaction. But which reaction uses energy? So the forward direction, the forward reaction. So the reactant, so basically if I increase the temperature, I'm giving energy to one side, and I know it's in the entire closed vessel, it's in the entire system by itself, but one side requires it, so they will use it. So if I increase the temperature, I'm going to increase the rate of the forward direction because it's consuming that energy. And how am I doing that though? We know, and I was reviewing our kinetics test, I'm almost done grading that for Qs. One question we missed on multiple choice was, if I increase the temperature enough to double the rate of the reaction, will it double the rate of the reaction? We say it should, right? Because temperature is when we say that we've increased it enough to double the rate of reaction. But there's all these other facets of the reaction that can tell us if the reaction is going to occur or if it's not, or if the collision will be effective or if it will not. What are two conditions to say if a reaction will be effective or not, or if a collision will be effective or not? Orientation and so the force of collision, which would be meeting activation energy, right? Okay, so we say, oh yeah, totally increase the temperature, it's going to happen. No, there's always this thought, this second idea of, is it colliding with the correct orientation, and is it colliding with with the correct activation energy? So if I increase the temperature, we know it's going to increase the rate of the forward direction. But what could possibly not still be met? Orientation and activation energy. But I will tell you, if I increase the temperature, there's a lot more collisions meeting activation energy. So there's a lot of them that meet activation energy just because I've simply increased the temperature and the energy. So that's why this one, there is no reversible, I mean, it is still going to reverse some, but it's not going to reverse significantly. So when I increase the rate of the forward direction, I basically said that I shifted right. Okay, when I shifted right, what happened to my relative ratio or relative amounts of products versus reactants? When I shift right, what happens to my relative amounts of products and reactants? Sky high, right? So I've actually increased the amount of products quite a bit. My reactants get consumed some, so I decrease the amount of reactants. All right, knowing what K's expression is, what happens to my K value? Does it increase or decrease? Increases. So I'm going to write that right here in green. Increases K value. Okay, that is the only one, the only variable that you can change that would increase K or decrease K. So, reminder, endothermic reaction, increasing the temperature. Overall, it causes the products to increase significantly because it's fueling the forward direction. Increasing products without changing the reactants that much, or even decreasing the reactants amount a bit, will leave K higher because the numerator is higher. And so here's a little bit right here in the reading or writing, whatever you want to do here. That gives you a bit more information. So more energy available to meet activation energy, more particles that will increase the reaction unidirectional because we're fueling one way and not the other due to the endothermic or exothermic nature of the reaction. A phrase that is great whenever you were trying to explain this in minimal words is this right here in red. Increase in the temperature favors the endothermic reaction. And not, and I'll say endothermic direction. That actually might make more sense. And that is a phrase they love to see on the AP exam. I've seen it numerous times on keys, like on the answer keys they send out. It's a very quick and easy way to explain. So I'm going to set up an exothermic reaction. I want you guys to tell me what's going on here. So A plus B equilibrates to C plus 100. So if I increase the temperature, you talk me through it. What happens? Not every one.
Increase the rate.
Increase the rate of what though?
Formation.
Formation of reactants or products? Not in this one. So if I'm increasing the temperature, the products are like, yeah, look guys, we got extra energy. Let's collide more often with greater activation energy, or with more energy to meet activation energy. So increases the rate of what?
Reverse.
Reverse direction. Okay, and so that essentially means I'm doing what? Shifting left. Okay, so shifting left does what to products? Because they're being consumed, right? All of these products are being consumed to make those extra reactants. So if you decrease your product concentration and increase your reactant concentration, what happens to K? K is smaller. K decreases. So it's a baby step, right? And I know you can go be like, yeah, increase temperature, shifts left. And you probably immediately can also determine that K is decreasing, but I want to give you some stepping stones if you need it. Okay, let's draw a graph and let's do a practice example. I think we'll be good here. Give me one more second. Mm-hmm. Okay, so do me a favor. I actually, pull your packet. I wonder if I printed this a worksheet for you. I'm the nice person to have. I'll just kind of stay down and mark those. I'm not a nice person. I'm not today. Well, it's fine. You don't need it. We'll do this one orally. Okay, so look at my reaction here, and I want you to tell me shift left, shift right, and then one piece of information that will give me some indication of what's happening. All right, so phosphorus trichloride is added to this reaction. Shift left, shift right, no shift. Everybody agree? We shift right. So basically, you're telling me increased reactant causes a shift right. That's because of what? Increased forward direction, right? The rate of the forward direction. What happens to the amount of chlorine gas when that shift right occurs? Huh? Give me. Okay, when it shifts right, you're telling me the reaction in the forward direction is occurring. What happens to reactants when they react? They what? Yeah, they definitely. So whenever you shift right, you're reacting these. When you react them, they get consumed to make products. So reactants are consumed. And if they're consumed, then the chlorine gas will decrease because it is a reactant. Okay, phosphorus pentachloride is added. Okay, so you're saying increase in products does what? Shift left. What happens to chlorine gas? Because you are forming it, right? As you consume products, you're forming reactants. Temperature is lowered. So temperature, and it's going to be related to our enthalpy and our enthalpy value. Okay, so so you're saying it's exothermic. If I lower the temperature, which way is it shifting? I hear both.
Right.
Okay, it is right. So it's because whenever you have, I'm just going to add energy here. When I add energy here, you'll see it as a product. I just want you to think of it as product. Do not write that on your exam. Do not even write on your exam for me, because it's wrong to say that. So if you decrease, it is wrong to say that, but that's how in honors chem you learn how to shift. So if you take away a product, you are going to shift left. I mean, this way, right, towards the product side. But it's because when you take away this energy, the reverse direction is declining. So reversing, I mean, the reverse direction is declining or slowing down. So the forward direction is going to be superseding it. So then you are essentially shifting right. What happens to the chlorine? Decreases, right? Because you're consuming it. Okay, phosphorus trichloride is consumed or is removed. Shift left. Neon is added. No shift because it is an inert gas. It doesn't do anything to the total. It does something to total pressure, but not partial pressures. Volume is increased. This one I might need to write. Increasing volume. What effect does that really have that we're concerned about?
Decreasing pressure.
Right. So my volume is this big. I increase it. The pressure inside is now lower. Oh no! I've decreased pressure. That's the stress that I've caused, right? Decreased pressure. What do I need to do then?
Makes more moles.
I need to make more moles of gas to re-increase the pressure. So which way will I shift?
Shift left.
Correct. So shift. So need more moles of gas. So I shift left. So these are not that bad. They're pretty easy. Graphically, though, we have to be able to represent this. So I'm going to give you a sample first and sketch what you need to, and then I'm going to give you 4 scenarios and we're going to graph it together. So you'll notice that this graph actually relates back to what other graphs we've seen maybe in our past units. Does this kind of look like a kinetics graph? Concentration versus time? Yeah, you're like, concentration versus time, because everything is related back to the rate of the reactions. This one, though, has a shift, the stress that's added. So when they're even, what do you know right now? When their slopes are equal. So rate forward equals rate reverse, so we're at equilibrium. So here we are at equilibrium. And then the stress occurred. So at time X, whatever, the temperature was upset. So they increased the temperature. So as they increased the temperature, what happened to the nitrogen dioxide? Okay, so I want you to tell me the reaction from this. That's what I'm going for here, okay? So if I've increased the temperature, and that caused nitrogen dioxide to also increase. Obviously, we're shifting towards the nitrogen dioxide. Does that make sense? Okay, so we're shifting towards the nitrogen dioxide. And we're shifting away from the dinitrogen tetroxide. Eventually, the equilibrium does reestablish. So tell me from here, is it nitrogen dioxide plus energy equilibrates to nitrogen dinitrogen tetroxide, or is it this? Well, I'll go this way. Let me call this number 1 and number 2. Why is it number 1?
Because when you add more energy on the product side, the rate of the products increases, which means that more reactants are going to be made.
Right, so you increase this, it's going to shift to the left. If it was this one, I would be consuming nitrogen dioxide, and I would be shifting away from it, so I'd be consuming it, so it would go down. So you could easily, maybe writing your own equations, pick out which one it does apply to. All right, I want you guys to make an axis. I'll go through maybe this graph in a second. Make a quick axis for yourself, and let's start our own. So I'm writing it opposite just because this is how I have it on my paper right now. Sorry. And delta H is positive 100 kilojoules. All right, here's our reaction. You got your axes drawn. What are your axes labels?
Concentration versus time.
Concentration versus time. I need more space. So concentration is in molarity versus time in seconds. Okay. Again, what does it look like when you're currently at equilibrium? Slopes are the same, right? So I'm going to start one here, one here. And this one is going to be, if I told you products were favored, so K value is greater than 1, told you products were favored, what would the red line be? The products, because products concentration are higher at equilibrium, right? So this would be products, and these would be reactants. And so I'm just, that's nitrogen dioxide, and the reactants is dinitrogen tetroxide. Okay, if I add nitrogen dioxide here, if I add nitrogen dioxide, which way does it shift? So it shifts away, so it's shifting towards this guy. All right, so what happens to, if I label this as the things, maybe it'll be helpful. Sorry, I keep changing colors here. So if I increase this, you're actually going to see a quick peak. It'll be like this. I'm increasing the amount of that. And then slowly, what's going to start to happen to the nitrogen dioxide content? If you tell me that I shift left at this point, it's slowly going to decrease, right? But as it slowly decreases, what is it making? It's making more of what? The N2O4, correct? So that one's going to be a kind of a not a quick jump. It's going to be a steady slope of incline, and then eventually they will reestablish equilibrium. Okay, so how do I know I've reestablished equilibrium? The slope is constant again. So what did I just say? I added nitrogen dioxide. You told me it shifted left, so it decreases the amount of NO2. It increases the amount of N2O4. Okay, let's say at next time I add dinitrogen tetroxide. What's going to happen to if I add dinitrogen tetroxide? It's going to shift right, okay? So I'm going to say at this point it's going to shift right, but what's going to happen to the graph?
It's going to do the same thing with the NO2.
So there'll be a peak on the other one, so there'll be a peak here, and it's going to slowly decrease as it becomes consumed, and then what happens here? It's going to have like a little hump where it increases, because as you told me, taking away dinitrogen tetroxide will increase the product here, so it's going to kind of like go like this. But as this starts to slow down, the rate of increase is going to slow down here as well. And these graphs are not like to scale by any means. I'm just giving you inflection points that we need to be aware of why it's occurring. Okay, so this was of the shift left part, or shift right, it was added dinitrogen tetroxide. Okay, next I want to decrease the volume. So I'm going to scooch out here so I have some more space. Decrease volume. And, oh yeah, that is balanced. So extend these out here. All right, so what happens if I decrease the volume? Shift left or shift right?
Shift left.
Why shift right? All right, so decreasing the volume
Increasing pressure.
increases the pressure, right? So I want to get rid of that increased pressure, so it's going to shift left. Sorry, I can't remember what you actually said just now. You said shift left. All right, so decreasing the volume increases the pressure, and you're like, I need to decrease pressure. The pressure is too high. I need to shift to the side with less moles of gas, so that's a shift left. Okay, so if I shift left, what happens to the dinitrogen tetroxide? Okay, is it increasing sharp or steady?
Steady.
Steady, because there's no increase of reactants or products, so it's going to be a steady increase. And it's going to level out. What's going to happen if I shift left? What's going to happen to the dinitrogen pentoxide?
Steady decrease.
Steady decrease. But is the steady decrease the same slope as this one? Why? I'm not same slope. It's going to be the same rate of increase or decrease as this one. Why? Well, it's because it's the two coefficient, right? So it's the ratio is saying this one is consumed twice as fast as this one is formed. So you can actually relate back to kinetics. I'm going to try to draw that. I'm not sure it's going to work. I'm going to draw it twice as steep. And, it kind of works. There you go. This is supposed to be 2 times the rate. Okay. Now we're back at equilibrium. You can see my values there. And I haven't even crossed lines that I very well could have here. I'm not sure. Now the last part, what have I not changed yet? I got reactants and products changing, volume, pressure decreasing, changing, temperature. So I want to make this increase temperature right here. Increase the temperature. So think through which way does it shift if I increase temperature.
Shifts left.
So I want you to tell me if,
No, it's just right.
okay, so it does shift right, correct, because this is an endothermic process, right? So I'm going to add it over here just for the visual purpose here. So if I have this energy and I increase the temperature, it's going to fuel the which direction? Forward or reverse direction?
Forward.
It's definitely going to fuel the forward direction because more, and here's the explanation part, more of the dinitrogen tetroxides are going to collide with effective collisions, aka activation energy. So that's why the forward direction is favored, and so I'm going to cause a shift right. So if I shift right, what happens to the amount of nitrogen dioxide? It's, right, shifting right is going to increase this product. And I know this one's a little bit different, but if I increase the temperature, it's a very quick increase in temperature, so it's a very quick increase in rate. Okay, so this one's going to increase pretty quickly like this, like kind of a straight in peak, and it's going to kind of level out, and it might slope down a little bit, but not very much. And then the reactants get consumed in the forward direction, so as they get consumed, they're going to slowly decline. All right, so at every peak here, or every inflection point, we have something else different happening. Something different. Which of these changes had a change in K?
Just the last one.
Just the last one. So here, and it's hard to tell really, but like these ratios, they're almost the same distance apart. Do you see that? From here to here to here. And so I was trying to do that as best I could to show that there's the same ratio of reactants and products, so there's the same K EQ value. This one, I didn't do a very good job of showing that, but it does, this ratio in the end does work out, but this ratio should be different. So if it's a different ratio, what happens to K actually in this one? Knowing that we're shifting towards the products, what happens to K? Does it increase or decrease? Increases K. Okay. We okay with that? All right. Go ahead and grab a Chromebook. I want your book so I can check it during this, but I need to make sure. Are you done? Did you finish yours? I need to make sure I answer all questions, so I'm going to instruct you first and then I'll grab those. Because there were more problems than I intended, and then I thought there would be. All right, and I'll show you guys where to go on my website, but you'll probably get 2 parts of this done today. The other part will get done later. I don't know why this is saying there's an error. So go to my website whenever you get on there. Go to Unit 7 Documents and go to Le Chatelier's Principal Simulation or WebQuest. And under Le Chatelier's WebQuest student, the document there is for you. There's some reading, there's some questions on there. The link for the rainbow simulations, that link that WebQuest simulation part that I really, really like, the Chromebooks I don't think are going to allow you to run Flash, which is what it runs. So I actually have a video of the simulation that I just voiced over because I was like, this simulation is really good. So if you want to do that last, that's totally fine. So there are 3 parts to the simulation, or to the document when you pull it up. Who's got it pulled up? A couple of us. Okay. So if you see that there, you can start on any part. The middle part's a lot of reading with some questions embedded afterwards. The last part are some multiple choice questions, and they're pretty challenging. So if you want to work with a friend on that one, that would be ideal. I want you to write this on a separate sheet of paper, And I want to see your lab notebooks, but who still has questions on their labs because they needed to get some clarification from me? Okay, I'll sit in the back and I'll come and let you guys ask me questions after you get started here. But I want to show you real quickly how this looks. So, oops. If you want to look up here first, I'll give you some hints here. So give me your attention in like 5 seconds here. Like 5 seconds. Okay. So this right here, you guys can read, and this is actually the pre-lab to a inquiry lab we're not going to do, and so that's where you'll see the similar formatting. Maybe. Let me scroll here. So this gives you some background, but like on your kinetics test, we're asked for real life examples. These are some real life examples you should be aware of, specifically for multiple choice and any like quick explanation based on concepts. So here's the YouTube video of my simulations. I don't know what I think this is actually posted. Is this on y'all's? Is this on yours? Because this is a Google Doc I pulled up instead of the actual document, so maybe I updated the Google Doc and not the actual document. I will get that for you in just a second. Animation 1, 2, and 3 have questions, and those animation link that animation is demonstrated on that video that I have on YouTube for you. It's also on my YouTube channel. If you just Google it, you'll see it. And then the strengthening understanding, that's a reading part. That one you can read fairly quickly. It gives you some indication of Le Chatelier's principle. So there's a lot of reading, not a lot of writing with this. Okay, you can write down the notes that you want to. The last part, or the last two parts, are based off some links, and then the questions are here. You might actually be able to answer some of these without looking at the links, but look at them if you want to. And part 3 is that multiple choice part that gives you some graphs, and there's 5 multiple choice questions, 6 multiple choice questions. Okay, so it looks really long. There's a lot of reading, but there's not a lot of questions. So work together, get started on whichever part, and I'll post this YouTube video under homework, I guess. This is homework tonight, textbook questions. This will be due on Wednesday, this simulation. So if you want to, yes. If you want to wait till Tuesday night, that's fine. Because there's not much for homework other than make sure you get those textbook questions done.
What's Tuesday night?
Tuesday night? Give me a second. Yeah, so this web quest is due Wednesday. So I would get done as best you can today and tomorrow.
We don't have a chance to do
let me see what, because we have a lab on Wednesday, and I need to get back to you by Wednesday, but I need to see them. Just let me post this video real fast. I really just need to see